Yes, so today we have Benjamin from KCL, who's going to tell us about ergodicity and hydrodynamic projections in many-body systems. Please go ahead.
Thank you. Excellent. So I don't know why there is this thing on top there that appears. So maybe, okay, something is being recorded.
It looks fine to me.
It's fine. Continue. There's this green. Do you see the green thing that appears there on top? Doesn't matter. Okay. I just play. It looks okay.
Good to me.
Okay, excellent. So yeah, so thank you very much for this invitation. It's a pleasure to give the seminar. So this is about some kind of a recent work that I'm doing, well, in particular with my student Dimitrios Anthologianis. And so it's going to be a seminar asking some kind of some questions, a bit some deeper question, if you wish, about statistical mechanics, ergodicity, and hydrodynamics. And the point here is to try to obtain results in quantum statistical mechanics, which are general enough, so general structures, and rigorous, mathematically rigorous. And it's very difficult, of course, to obtain rigorous results. And I think, it's my opinion, why I'm into that, is that looking for the rigorous result can help a lot to kind of characterize a bit more what is possible and what is not possible in many-body systems, interacting many-body systems. Especially nowadays, there's a lot of phenomena that are being discovered. There's a lot of kind of new phenomenology that go beyond kind of what people thought about previously. For instance, okay, in the context of hydrodynamics, something on which I've been working a lot. Of course, there's hydrodynamics for integrable systems, which is very different from the one for non-integrable systems. There's concept of scars that appear, there are oscillations that are seen sometimes in quantum evolution, something like looks like lack of thermalization, lack of ergodicity. So there's the question: what is possible? You know, how far can you get, and how can you constrain time evolution and dynamics in a quantum many-body systems? And so this is kind of the question that I'm asking here. And so I'm starting. So basically, there's a lot of possible many-body dynamics. Okay, and here I'm going to be thinking about Hamiltonian dynamics in quantum lattices. Okay, so spin lattices, or it can be a chain or high dimensional lattice, say ZD. But apart from that is a complete general. I'm going to be asking questions about what can happen. And of course, depending on what the Hamiltonian density is, so I'm going to be thinking about local Hamiltonian density, meaning that h of hx is supported on few sides around x. In fact, the whole thing works as well if hx is supported on an infinite number of sides with some kind of decaying envelope, some kind of quasi-local things. But for now, just a few sides is sufficient. And of course, if you take hx to be just sigma xz, or the z polymatrix, there's not much dynamics that happens, right? So this is just evolution on each side separately, independently. If you take it interacting, for instance, you take this Heisenberg lattice, where you have a interaction between neighboring sites, then something non-trivial happens. And here you would expect, in this particular example, in dimension D, you would expect something like hydrodynamics phenomenology to occur under quantum dynamics at large time. But this is typical interacting system, and if you have integrable system, then it's a very different phenomenology. It's not the usual diffusion hydrodynamics. There's a lot of ballistic components now and this is a different model where it's very different things can happen. And also, there's a time crystals that have been studied under certain things seem to even not thermalize, and there are oscillations that seem to occur and to be stable at very large times. And then you wonder, okay, so what is possible overall with this quantum dynamics? Okay, so what are so I'm going to start by describing kind of mainly just in words the main results, what I want to get to. Okay, so the main things that I want to get to, and then I'm going to explain a bit what we mean in all that and how we get to that. Okay. So, so the question is: are there general universal results that we valid in all these cases, even if these, these like various special cases I'm showing there are very different? And so trivial inside dynamics doesn't do anything. Integrating system has, some standard conventional type of hydrodynamic behavior. Integrable systems have a lot of ballistic modes, so very different behavior. But are there results that are valid in all cases? Can we constrain a bit what is possible? Okay, so this is a question. Okay. Now there is a result. So the first thing I want to talk about is how operators behave as you time evolve them with the local Hamiltonian. Okay. So something I call operator thinning, and I'm sorry, actually I changed a bit the title of my talk. There was something called operator ergodicity in the end. I don't think is the right words. Anyway, the words are not that important. I'm going to explain kind of the concept, what I mean about that. Okay, but here I'm calling it operator thinning. So let me recall one of the most important basic and rigorous and general result about quantum lattice models, and is the Lie-Robinson bound. What is the Lie-Robinson bound? Well, it tells you a bit about how an operator, say A, let's think about that as a local observable in the quantum lattice model, how it can grow with time. Okay? So if you evolve it with the Hamiltonian, it's the IHT, A minus IHT, and you try to see what it looks like at large time, well, of course, H is supported everywhere on the chain. And so as soon as you evolve it a little bit, in principle, this new operator, A of t, that is written there, is going to have components which are non-trivial everywhere on the lattice. Right? So it's not supported anymore on just fused lattice side as soon as you evolve it a little bit with time. It's supported everywhere. It has non-trivial component everywhere. But how strong are these components everywhere on the lattice? This is what the Lie-Robinson were asking in, I don't remember now, in 70 something. And the way that they were asking the question was, okay, let us try to take the commutator of A of t with some other local observable, I call it B. Okay? And let's look at the modulus, the operator norm of that commutator. And they say, well, okay, this actually, because the Hamiltonian that I'm using to evolve is local, is the sum of local densities, this will have to be bounded in a very specific fashion. It's bounded by some constant, then it's an exponential decay. And exponential decay with lambda that is positive, exponential decay is in terms of the distance from A to B minus a certain velocity times time. So what does it mean? It means that essentially A is non-trivially supported on some disk of radius Vt, but beyond that, beyond this distance, it has very little support and commutes with almost commute with everything else. So that the special growth of this operator is limited. There's a bound, this is the Lie-Robinson bound. And that's true completely generally. Okay. Now, of course, it is obvious, this is completely obvious if you take the trivial dynamics, there's nothing to say, because with the trivial dynamics, A of t does not grow. Okay, so the non-trivial thing is that it's also true, stays true with the non-trivial dynamics. In fact, later on, it was found, shown that if you apply this operator norm result in thermal states, then you have another result. And the result is that you have a similar exponential decay, but not for operator norm, which might seem a bit abstract, but for actual correlation functions, A of t, B. So essentially, B does not correlate with A of t, B is far enough from A, far of the type V times t. Okay. Now, the velocity that's there is called the Lie-Robinson velocity. It is defined with respect to the evolution Hamiltonian purely. And it is an upper bound velocity, because in fact, in these correlation functions, they actually decay exponentially with a velocity that is usually smaller than this Lie-Robinson velocity. There's another velocity, and that smaller velocity actually depends on the state. So when you look at correlation functions, the support of A of t is actually very much controlled by the state. So correlations decay exponentially, but with a velocity that is smaller than this VLR in general. But Lie-Robinson said whatever velocity is, there's a maximum, and it's that velocity, Lie-Robinson velocity, and they have an operator relation. So this is kind of some of the basic results. Now, it's not basic results about dynamics. Now, there's a lot of other results in quantum statistical mechanics about states and all that, but in fact, there are very few rigorous results about dynamics beyond this one. So, well, people have generalized that beyond quantum lattice models and beyond the Z2 lattice. Of course, there's a lot of generalization. But all these results are bound on what the operator norm can be beyond certain region. But inside the region, it is very difficult to know what's happening. And this is an interesting question. What's happening inside that region where the operator, the special growth that determines the special growth of the operator. Okay. So this is part of our results that we know a little bit more what's happening inside the region. And I'm not going to write it precisely, I'm going to write it precisely a bit later, but essentially the intuition is that if you have an operator that's start on some site and you evolve it and then it grows in space, well, somehow it cannot grow in space and then be very, very strong everywhere. Somehow it's got to thin up in a sense, right? It's like, it's got to decompose into a smaller number of things and be thin. So we have an expression of thinness. So the operator A of t is indeed thin. So, meaning that its commutator with other observable is very small, almost everywhere within this range of growth determined by the Lieber-Wilson velocity. Almost everywhere is not necessarily everywhere. And of course, if you take the trivial dynamics, it is not at the point zero, because trivial dynamics, the operator stays at the point zero. It doesn't thin up, right? Or thin down, it stays at the point zero. But it's still very, very thin everywhere. But what we're saying is that almost everywhere is going to be thin. And so the velocity at which it's not thin are going to form a set of measure zero, essentially. Okay, so it's a very much kind of decays a lot of things go away. Okay? There's also related to that something which one can call almost everywhere ergodicity. So ergodicity, I'm going to come to that now, is naively or perhaps intuitively in physics understood as time average being equal to ensemble average. Well, there's something like that as well. As a consequence of this thinning, time average of the observable, almost everywhere in space-time, with respect to velocities, reproduces ensemble average in a certain fashion. I mean, the results are not extremely strong, like you take time average, you get ensemble average always. It's not exactly that, because these results are supposed to be valid for every possible dynamic. So they cannot be complete. There are certain dynamics that that are very so special that not a lot will happen. But almost everywhere, so no matter what you do, even if you have a complicated local Hamiltonian, there is some kind of notion of ergodicity that appears. Okay, so I'll explain what it is a little bit. And more than that, you can look at this not just in terms of time average, but you can do that at any frequency. And there's also a thinning that happens at every frequency. So one can look not just at large time average, time average over a large period of times, but one can also do that at every frequency and thinning still holds. Okay, so I'm going to express this result very soon now. But this is the first type of result. It's looking inside this region of growth of the operator, where there is not a lot of results. Now, this result is interesting. In fact, the way why we came into that was to get to the understanding of hydrodynamics, actually. And it turns out that this is related to hydrodynamic projections. So what does it mean thinning? So if the operator, there's not a lot left within that region of growth, then a lot disappears. And then you would say, well, okay, what remains? There's a lot of information that is lost, and there's a little bit that should remain. Turns out that the way it disappears, the way things decay, is controlled by something that looks like hydrodynamics. Now, if you think about physically about this correlation function, A of SB, okay, so you have some operator at zero, you evolve it in time. And then you try to look at the correlation with some other operator. A cartoon picture of that is you have your surface of water, in your bath or something, and then you put your finger at zero there, and then the surface of water is disturbed there. So there's an observable, there's a disturbance there. Disturbance evolves in time and produces waves that grow on top of that. This is the little picture that where I have the wave that grow around a certain point. Okay? These waves, well, this is the domain of influence of that operator that grows with time as time evolves. So it's very much like a Lieber-Wilson velocity type of bound. Okay? But here it's a hydrodynamic phenomenon. Okay? This grows, and these waves then is what produce the largest amount of correlation with another observable. Now, if you disturb the water a little bit, there's always a lot of correlation, because there's a lot of information that travel very fast. But the largest correlation travels slowly and is controlled by these waves. And it is the waves, no matter how you disturb the water, they are of a very specific shape and they produce very specific correlation. So these hydrodynamic waves represent a reduction of the number of degrees of freedom at large space-time. And these wave fronts are what control the leading leading asymptotics of correlations. So it turns out that they are related to this operator thinning. In fact, operator thinning is what allows us to show a more general theorem, which says that correlations are due to propagating waves. Now, this is the naive picture of hydrodynamics. And of course, if you have a general many-body systems, a lot can happen, right? I mean, if you have a typical interacting, non-integrable system, you expect kind of ballistic wave to produce a leading correlation. If it's integrable, well, what you discover is that the concept is still valid, but now you have an infinite number of ways for all the ballistic modes. And in fact, this idea that hydrodynamics works even for integrable system actually points out to you that, in fact, hydrodynamics does not need the system to be chaotic. You know, an integrable system is not chaotic fundamentally. It does not need that. It's not related to chaos. It's not related to that. It's related to something else. It's related to many-body dynamics, quantum or classical, actually. So you look, this is a general concept, and that's what this result actually says. This is a completely general concept. It doesn't matter what your system looks like. No, it's a completely general concept. And the result says, following it says that if you look at the two-point function of an observable A, then you put it at a space-time position xt and try to correlate with B. Right? Take the correlated two-point function, and under appropriate averaging, the averaging can be at any frequency. So this is hydrodynamics at any frequency, not just at zero frequencies. The averaging can be at any frequency. There is a decomposition of this two-point function in terms of objects where you project the operators A and B onto an appropriate space of a measured degrees of freedom. It's a space, you know, that one can define. These projections one can define. And what's in between is just something that represents propagation of the conserved densities for this appropriate frequency. So there's a hydrodynamic projection that will describe leading large space-time dynamics of two-point function, but not just large space-time at zero frequency, but at any arbitrary frequency, in fact, also arbitrary wave number. And this is, so it's a projection onto emergent waves. It remains valid in all cases. So even this dynamics is completely trivial, like nothing happened. It stays on point, like it completely factorizes into every side. This still is true. But of course, the space of emergent waves depends. Okay, this also holds at every frequency wavelengths, but the properties of the dynamics are all within that space of emergent waves, naturally. I mean, then this is a non-trivial thing. So if you have a dynamics which is trivial, which stays at one point, then this space of emergent waves have a very special structure which you can work out and is very simple. And that formula then just represents a very simple result that you can obtain in different ways. If your system is integrable, then these emergent waves are the large number of constant quantity that you have in your model. If it's not, then it's a restricted number of quantum quantities and all that. But in any case, there is always a way of describing the large space-time. The reduced number of freedom, and how reduced is your number of degrees of freedom depends on your dynamics. It's something that you have to work out. Okay, so these are kind of just in words, the two main results. And the second follows essentially from the first, although I'm not going to give the derivations. Okay. So you have any questions about just these words? So by the way, don't hesitate, please, to stop me at any time if you have any question. There's no set amount of material that I have to go through. I mean, whatever I have time to go through is fine. Okay. So now let me be a bit more precise. And
Sorry,
discuss...
yeah. When you say the leading term looks like this, what is this small parameter that you have in mind that determines?
Yeah. So this formula is not precise. So the small parameter is 1 over the scale. So the scale is here large time. So small parameter is 1 over t. And the way that function will decay in time, and the way that it decays, well, typically with the way it decays depends on the structure of the waves, if you have a continuum or not, now that. And basically, you take a large time limit. It's a large time limit. I come to the precise formula. You see, there's a precise. You do this large time limit, black, you get an equality. Yeah. One question. Okay. Yes. Okay, so let me, so before I go to that, so there was hydrodynamic projection, then there was the idea of operator tuning and ergodicity. I want to talk about the notion of ergodicity. Ergodicity is a word that has been used a lot in physics and kind of used in all kind of ways. And there's a lot of possible notions of ergodicity. I mean, the first one in classical mechanics is the one about your trajectory being dense in the phase space. Well, this picture is not excellent if you just have a model with one position and momentum and nothing else. As it evolves, it will stay within its energy shell, for instance. So here I didn't show the energy shell. But anyway, you imagine you have your many particles model, it evolves as the trajectories, and these trajectories become dense in phase space, or at least on some subset of phase space. Okay. And then what it says is that, the idea is that with the time average of any observable, here's function of x and p in classical mechanics, time average should be reproduced by the ensemble average. That's ergodicity. Right? That's the main thing about ergodicity. And this ensemble average is basically an integration over phase space with an appropriate measure, and typically the measure would be supported on these sub-manifold of phase space, which corresponds to fixed energy, say, or fixed, other kinds of quantities. Okay. In general, it's well supported on some hypertorus in phase space corresponding to all the kinds of quantities that are available. And that's your notion of ergodicity. Okay. Classical mechanics. Now, this is not excellent. I'm sure it's not the right concept, but not excellent. It's hard to deal with in quantum mechanics because, of course, you don't have precise trajectories in quantum mechanics. Well, you can actually make a notion of trajectories and ergodicity. There's work on that, but certainly in quantum lattice models, it becomes even more difficult to talk about trajectories. And also, perhaps more deeply, it's also not quite the right concept in statistical mechanics, quantum or classical. In statistical mechanics, you think about taking infinite volume limit, and then you have an infinite dimensional space, and you still want a notion of ergodicity. So you still want that a time integral, at least in the classical case, would reproduce some measure ensemble average in statistical mechanics in your infinite, your system with infinity degrees of freedom. However, it's very unlikely in infinite dimension that the time integral over short time scale, this is what we expect, ergodicity to happen over short time scale, very unlikely that this will cover the whole infinite dimensional space. Now, of course, you have to perhaps have a notion of how far you are from every point, a notion of distance, and maybe you become less now that, but it gets a bit tricky. And in fact, it is actually tricky, and you need to be careful about what you mean by covering the hypertorus in your infinite dimensional space. It's not quite the right concept, because in fact, it's a bit difficult to work on. It's concept of ergodicity. There are other concepts of ergodicity that people have come up with, or at least they give name ergodic to various things in quantum statistical mechanics. Let me go over that, because these are important concepts. Okay? One of them is the concept of ergodic state. So an ergodic state, what it is, well, in quantum statistical mechanics, first of all, a state is just some positive linear functional on an algebra of observable. It's something that when you take an observable and apply this on it, you get a real number. The real number is its average. Yeah, that's the state, right? The state is just taking the average of observable, right? Now, an ergodic state in quantum stat mech is the following. So first of all, you assume it's homogeneous in space. I mean, this is just for simplicity. There are notions that can be valued without that. But for now, assuming homogeneity in space in a way for the Hamiltonian evolution. Okay? And what it says, ergodic, it says that if you are to average an extensive quantity, something that's integrated over all space, then that should be non-fluctuating. Now, if you have, in other words, from the thermodynamic point of view, you have a single phase. So it's not like spin, it's not a sum of two states where the spin cannot be up and the spin cannot be down. It's a single one. This is what people call ergodic state. So mathematically, if you take the average over a little square, subsquare of linear length here, 2 plus 1, and you take its variance, so take the average of its square. At large L, that should go to the square of the average, which is just a square. Okay, that's notion of ergodicity in quantum is true. Now, it's not quite ergodic in the sense of time averaging, right? This is ergodic in the sense of space averaging. So it's a bit of an abuse of the word ergodic. In any case, it's a useful concept. And so let me go there. So this is one of the possible concepts. Now, it is true that if you look at Gibbs states, these are ergodic according to this notion. So take a finite temperature state. So again, there's no time evolution here, so it's not ergodic in that one. But okay, take a finite temperature state, exponential minus beta h. And yeah, take the infinite volume limit of that, and the infinite volume limit exists and behaves nicely and all that. It gives you a state in your quantum static model. Okay. And it turns out that this limit exists. It is unique if your temperature is high enough. In 1D, it is unique at any non-zero temperature. But in higher D, well, if it's high enough. And there are known theorems for that and known values of beta 0 for which you are sure that it is unique. And that's because, of course, if the temperature is too small, you can have phase transitions. And then maybe the limit is not unique and you would need to specify the boundary conditions to know which phase you are. But in the case where it is unique, then we know it can be shown that this state is ergodic. So if you calculate the average of a large observable, the variance of a large observable is something that goes to 0. Okay. In fact, more than that, it is actually what is called exponentially mixing. So mixing, it says that the 2-point function, connected coercion function, decay. So it's not just that the large observables don't fluctuate, that 2-point function decay very quickly enough in space. And one can show, it's not too difficult to show, that exponentially mixing, the last equation that's written there on the page, implies ergodicity. So if you take your A, B, and then you kind of average A over a large space and average B over a large space, and you assume indeed that the connected correlation decay very fast when the A's and B's are far in space, then most of the contribution of these averages will come when A and B are near to each other in space. And then you get, when you divide by the volume square, essentially you get 0. And so the connected coercion function average over space will give you 0, and that will give you the ergodicity statement, the equation there at the bottom of the page. Okay. So this is mixing. So the Gibbs states have the nice property of what they call ergodic state. Okay. Another important thing is the decomposition theorem. So you say, well, okay, ergodic state, why not? They have they agree with the experimental idea that if you measure a large quantity in your thermodynamic state, it's going to be almost surely what you measure it in once. This is going to be the right thing. It's not going to fluctuate a lot. But there may be other states, and other states will be kind of combination of that. And there's also this theorem that any state, homogeneous state, is a mixture of ergodic state. This is a theorem that says that any state is going to be some mixture of pure phases, pure thermodynamic phases. So you take any state, you can always express it as an integral, in general it will be an integral, over all the possible ergodic states, those that factorize at large distances and that have vanishing variances of large observables. Now, this is very similar to writing in quantum mechanics a mixed state, a trace, as a sum of pure states, kind of an energy eigenstate, if you wish. Okay? A mixed state can only be written as a sum of pure states. This is a similar phenomenon. And in fact, the similarity is relatively strong. These ergodic states are kind of the pure state from the point of view of statistical mechanics. They are what is sometimes called extremal states, though the states form a convex set because you can always add them with positive coefficients, and then the extremal ones are those that cannot be written as a sum of other things. And it's like the pure state in quantum mechanics are also extremal state. So it's very similar to that, but it's a little bit different. It's not the large volume version exactly of this expression, but it's very similar to that. Okay. It does in general, if you calculate the average of a square of a large observable, it will not separate, but it will into the product of average, but it will be an integral over all the possible states. And then if you have a state which is a combination of say you have a phase you have a phase transition, and then first order phase transition, and you have two possible states at a given temperature where all spins are mostly up or all spins are mostly down. Well, if you have a sum of these two states, then you're going to see fluctuations of your total spin. It will fluctuate up and down. And this expression that you're going to see non-trivial variance of this total spin. Okay, so this is the notion of ergodicity. There's another notion of ergodicity. It's called the ergodic principle. And that goes a bit beyond. It's not rigorous or stated, rigorously proven nor stated. What it says is that any state that is homogeneous, that is stationary, so invariant on the time evolution, and that is ergodic, like that we've said, so that whose large observable don't fluctuate. Well, it must be of the Gibbs form. So we said previously Gibbs form are ergodic. Now it's the opposite. It must be of the Gibbs form. So it must be some state, of Gibbs form for some Hamiltonian H, which might not be, H prime, which might not be H, but anything that commute with it. For instance, perhaps a generalized Gibbs ensemble. In fact, this is a very important notion, which unfortunately has not been proven yet. And this is a notion that if one can at least state it or prove it or understand it better, one will get a better understanding of the generalized Gibbs ensembles. So basically, what does it mean for a state to be a generalized Gibbs ensemble? Well, it's connected to that. In fact, perhaps the best thing is to define all the generalized Gibbs ensembles, so all the states which are natural states that you obtain after relaxation, to be those that are homogeneous, stationary, and ergodic. Okay, so that can be taken as a definition, if you wish, of the generalized Gibbs ensemble. And that you see in this definition, there's no involvement of explicit conserved charge or anything like that. All you ask for is homogeneous stationarity and the additional notion of ergodicity, which is kind of related to the fact that your density matrix is exponential and things decay at large distances. Okay. So these are kind of two notions of ergodicity that appear in quantum stat mech, but as you see, they don't involve time. Well, involve time in the sense of stationarity, but don't involve time average. Okay. But I'm going to start with this ergodic state and see what happens with ergodic state and what we can do. Okay. Now, I should just make a parenthesis. I think it's an interesting parenthesis that actually ergodicity, as stated there, in the big version of the eigenstate thermalization hypothesis. So there is something into it that indeed has to do with ergodicity. Okay. And suppose you have a Hamiltonian which is not integrable. Now, a not integrable Hamiltonian, the only meaning that we can think of is that all the GGEs are just the thermal ensembles. Okay. So it doesn't have any other conserved quantity. It might have perhaps spin being conserved, but that's kind of an easy addition to that. Suppose it doesn't have any other conserved quantity. And as I said, the GGEs, we can define them perhaps as the set of homogeneous stationary ergodic states. So suppose H is not integrable, it means suppose that all the ergodic states are just the thermal states. Okay. So this is, here the notion of not being integrable is difficult, and this is kind of putting that difficult notion a bit under the carpet by saying, well, the ergodic states are thermal states, but it's probably the most precise notion of a system not being integrable that, that one can write. Okay. Then if you take a sequence of eigenstates and find volume and take the large volume limit, and suppose that this sequence is something that converges, then what you get is a state in infinite volume. Okay. Now these are all eigenstates of the Hamiltonian. You can do that. Now the eigenstate thermalization hypothesis will tell you that all of these eigenstates of the Hamiltonian, given energy, they are very near to a thermal state. And in fact, when you take the infinite volume limit, it should produce exactly a thermal state. Well, we know that by the decomposition theorem, that state will be decomposed into a sum of possible thermal states at all possible temperatures. Okay. Now, if the state that you get is ergodic, then you know that, sorry, there should be a measure. If I look in that last equation, there should be that there's some measure there that you don't necessarily know. But if the state is ergodic, then you know that there can be a single temperature. There can only be a single temperature that's there, because these are all the ergodic states. And the temperature is fixed by the average of the Hamiltonian density. That means that if you have ergodicity for that sequence of states, then you have the weak ETH. So in other words, if you really want to prove this weak version of ETH, all you have to show is that the energy eigenstates at large volumes are ergodic according to this quantum stat mech definition, so that the average of large observables don't fluctuate, have zero variance. Now, this is actually a difficult problem. It is not clear how to do that. And even if we had the relation between ergodic state, decomposition as an ergodic state and traces, it is not in general true. Well, in generality, it is not true that a given energy eigenstate is ergodic, and proving that in this special circumstance of A should not be integrable as to finish. But that is at the heart of the eigenstate thermalization hypothesis. Okay? Now, so this is kind of putting a bit of a flesh on this notion of ergodicity. Okay? But these notions do not involve time evolution, okay? And it would be nice to see if time evolution, if time averages can be seen as reproducing somehow unstable averages, in the ergodic state. This is what ergodicity should mean. Okay. Now, ergodicity has to do with time average, and ergodic state is a state that has certain properties. Still, there's a relation between these two. Before that, are there any questions about notions of ergodicity? So here we go to indeed time domain ergodicity. So time averaging. Okay. Now this is the result that we have. So we say, okay, let us start with some ergodic state which have these properties. Okay. And let us assume that the state we are looking at is some countable mixture of ergodic states. So it doesn't need to be ergodic state, but some general state. Except it's not necessarily just an integral of all these ergodic. We need a countable, something that's countable. It's some kind of mathematical restriction that we have. But so anyway, it's some kind of very large family of states. So they are homogeneous states, and we assume that they are also stationary with respect to some Hamiltonian evolution. Okay. Then it turns out that for every frequency omega and every wave number k, for almost every speed v, so the speed in space-time, and for every rational spatial direction in space, I have some pictures soon, then the following holds. So the commutator of the time average of this observable with anything else is zero within that countable mixture of ergodic states. So this is something that is true for any of these states. So, you just need very weak property on the state. It is not a relation for operators. It's not like the Lieber-Benson bound. This is weaker than that. So kind of a weak version of commutators going to zero. Okay. What it means that if you take your time average of the operator A at position which are vt, so along a velocity, and time t, and here the position you need to take the integer part because you're on the lattice. So you take integer part of every every element along a certain direction. So there is an n there that should be there. So it's v and t, so it goes in a certain direction. Okay. And then you take that time average, but with respect to an arbitrary frequency omega and arbitrary wave number k. Okay. So you look at this operator, how it oscillates in time, and you look at how it oscillates in space. Okay. If you take that operator and commute with b, so this commutator will go to zero at large time. So the operator cannot grow very much in times. Within that region where it is supported, it still cannot grow very much. It is still bounded to some extent. If you observe with anything else, not only it is not bounded, if you observe with anything else, you take the commutator, that will go to zero. So now this is true for almost every speed v, and for, as described there. So not for every possible speed. So not necessarily, for instance, purely in the time direction. If you take v equals 0 and go in time direction, it might not work, but in the neighborhood of it, it will work. No matter how close to it, it will work. It will go to 0. There's a similar relation that works for these ergodic states, not for this combination, but for these ergodic, very special states that have vanishing variance of large observables. And that then really tells that they are ergodic. Basically, what the relation is that if you look at the connected correlation function at large time, that also goes to 0. Now, this is a large time limit, okay? But under arbitrary oscillation in time, in arbitrary oscillation in space. Okay. So this holds. So if I look at the little graph representing that, you look at your A of t, it grows, in space as time evolves, but so it grows in extent, but it cannot be very strongly supported everywhere. It cannot. It has to be such that if you try to time average it over large time with some frequency and look over large space at some wave number, that should go to 0. And that holds on the quantum lattice for every rational direction. So every direction that you can form by pointing from 0 to some point in the lattice. this is a dense subset of the unit sphere, all these directions. Okay. So basically, by these results, then the time domain average, so average along a ray in space-time, is non-fluctuating in these ergodic states. So we take the large time limit of the average, the nth power of it, you're gonna get the n power of the average of the observable itself. That's a consequence of this equation lim t of a bar tb connected equals 0. So that consequence of this is that you can go to the nth power and find that the n power always average of the n power I always give you the n power of the average. So this is a notion of ergodicity. Essentially, something does not fluctuate in time under average in time. That's kind of a slightly nearer to the usual notion of ergodicity. And this was not known before, so it was known that ergodic, so it was by definition said ergodic states are those whose observables which are kind of integrated over a large average over a large region in space don't fluctuate. But here it says that, well, this is also true in the time domain. So that what with the operator is very much constrained. The operator cannot grow forever. Yeah. Any questions about that?
Yeah. Question.
So if I, yeah. Question.
Hi, Benjamin. So you don't have any notion of you don't use any notion of locality for the Hamiltonian.
So yes. Notion of locality is crucial. In fact, for the Lieber-Rosen bound, also you have a notion of locality. So the Hamiltonian, I see it as a sum over local Hamiltonian density. And with that, and only with that, this holds, otherwise it doesn't hold. In fact, locality, this is also an interesting point. So people have tried to push that as much as possible. And the Hamiltonian density does not have to be supported on few sites. It can be supported on infinitely many sites as long as the operator norm of the Hamiltonian density decays fast enough, around the site where it is positioned, right? And then you have a sum over all these positions. So, and that holds also for these cases where you have a strong enough decay, and the usual strong enough decay is exponential decay, and there's all so that will hold also there. But yeah, you need the locality, otherwise it's yeah. Other questions? So this is
I have one.
Oh yeah, go ahead.
So, but I guess you have a statement about corrections or, the scaling of cumulants or something like that.
So we don't have, this is of course a good question, since this is a bit, I also have to admit a bit new, there is a scaling of cumulant, and one should look at, for instance, a large deviation function for that, or something like that. And we don't have, but the hydro projection is a little bit of that for the second cumulant, if you wish. Okay, so there's one would have to generalize the hydro projection to higher cumulants, and we don't know yet how to do that. For now, we don't have a full understanding of the corrections. But thank you, that's a good question. Yeah, the hydro projection is something that wants to go in that direction, so to speak. So I'll come to the result. Okay. Other questions? Okay, so I should just mention, so it's an interesting kind of point, I think, remark to make. Of course, if you have, you can make a very simple calculation here. Take a finite volume system, quantums, lattice and finite volume. So this is just a quantum mechanics, with the finite dimensional Hilbert space. Okay, and then suppose you take the limit to infinity before the limit volume to infinity. It's very different. So that would be the case, like I was saying at the beginning, where you do ergodicity on your not your statistical mechanics, your model with a finite number of degrees of freedom, and then you kind of you are dense in your torus. And in statistical mechanics, it's very different. You never get to be dense in the torus. It's a different principle. So here you can see it explicitly. So what's happening? Suppose you take 2 to infinity before volume to infinity. Now let me assume for simplicity that the Hamiltonian that I'm taking here is again not integrable, and so all the energies are non-degenerate. Okay, for instance, it's a strong assumption. Of course, you can generalize that to a weaker assumption. And then let me take just the average of A of TB, just two operators here. There's no notion of locality that is necessary here because it's just quantum mechanics. Okay. the time average, the time integrals, sorry, this question is not excellent. So what I meant to write here was a time average, not the time integral, time average, not Fourier transform a time average. But in any case, you've got to, if you do it properly, otherwise Fourier transform, you get some infinity integral. So the time average, okay. What you do, well, you can decompose into energy eigenstate. That's the first step after the first equality. And if you do that, you see that if you do time average of this, well, E minus E prime, you're gonna get 0 because of this oscillatory term, except when E equals E prime, and then you get the product of A and B. So this is a very simple example of time average of observable. Product of time average gives average of product. Now, if I want to do the full thing, I'd have to time average over B as well, but that doesn't change the result because on the right hand side I time average over B, and I get nothing different. Okay. So this ergodicity in terms of time average of two-point function is completely trivial in quantum mechanics. This is immediate. There's no computation to be done here. But here, what we're doing is something different. We take the volume to infinity first, before the time to infinity. And then is this notion, and this is kind of a picture type of notion, is one has to calculation, but basically the trajectory, so it does not have time to cover the whole phase space. So it's not obvious that you do have this separation, that time average observables are non-fluctuating. So it's not obvious that this holds, and you need to do kind of non-trivial computation to do. So instead, what's happening is that you have the concept of locality is crucial here. Locality is absolutely crucial, is a question Masoud asked. I mean, it's actually crucial, and there's some kind of local decoherence. So you look at local observables, and there's information that's being lost in the large distance at infinity. And that's why you can get some kind of ergodicity in statistical mechanics. And that's why you get a theorem that looks a bit like that, but it is weaker than that, certainly much weaker than that, right? Because it's just, for almost all velocities and all that. Okay? So, so this is a comparison, and that kind of brings on the point that it's very different in statistical mechanics, ergodicity, than it is in system with finite degrees of freedom. And that difference has a consequence in that notion of ergodicity in terms of time average. Yeah. So I think it's an important point to make. Now let me go to the Hardy projection. It turns out that this notion of ergodicity allows you to show hydrodynamic projection. So I don't know how I'm doing in time, but okay, I'm a bit close to the end, so I will go a bit quickly there, but at least express the result here. So basically, we want to know how this decay happens, a bit the question that one people was asking, and basically we want to know the leading asymptotic behavior. Now, would like to know it everywhere within that region of growth, or special growth of the operator. Okay? But now this decay depends much more on detail of the state. So we don't have results like of the type commutator of operator. We have results just in ergodic state. It depends on the detail of the state. And basically what's happening is a generalization of this basic physics of measuring waves and hydrodynamics. Okay, that thing I was thinking. So at B, you make a little disturbance. Disturbance is complicated, but then there's relaxation, there's ergodicity, and there's something simple that comes out of it, which is just a wave propagating, perhaps expanding diffusively or something else in space over time. And this is what the observable A will see at large time, and this is what produces the leading correlation. Okay. So it's a generalization of that. Now, the wave represents the slowly decaying modes in hydrodynamics. So basically you understand them in terms of the conserved quantity. So you say, okay, you have some conserved quantity, Qi, which is a total integral of some local density, something local again. That local density satisfies a conservation equation. And this conserved quantity then comes with the Hamiltonian standard thing. Okay. And so these waves are essentially these Qi carried on. Okay. Now there is a Hardy projection formula. This Hardy projection was actually, certainly spawned, Herbert knew that, the people before, it's been written in various ways. But with our ergodicity, we managed to prove it rigorously. Okay, so now it's a rigorous proof, but using this ergodicity thing. Okay. And what it says is the following. So it's really that little picture, right? But it's a mathematical equation. Okay. It says that you evaluate the two-point function, axt b00. This can be written in terms of two-point function of the conserved densities only. So it's a reduction of number of degrees of freedom. Okay. And a two-point function here should be a connected two-point function. So although the connected doesn't matter too much, it cancels out on both sides, but usually it's connected to one function K. So arbitrary operators can be written in terms of conserved densities. That's the idea that the correlation between operators that are far from each other is transmitted by the conserved density. So it's just written the correlation function between conserved densities. Okay. And what's this? What are these terms? So the AQI is the connected two-point function of A with the total charge QI. So this is some kind of projection. CIG is just some matrix, which is the inverse of the susceptibility matrix for that particular state, for this particular system. Right? So this project produces a projection. The QI is your basis, and then you kind of you project, and you have to invert the basis in a way. So it's kind of a simple basis expansion. Okay? But it turns out, so what we can show. So this equation people have written many times, but it turns out that this is true and rigorous, valid under this type of time average and spatial average. So basically, you take a time average, it's like taking a large time limit, long time limit, and also you look at your function at small wave number, something that goes like 1/t. So wave number going like 1/t, that's the Euler scaling, which is ballistic scaling. So this represents the ballistic modes propagating. If your model does not have any ballistic mode, then what you find is 0 equals 0. So that just tells you the bit corresponding to ballistic modes. Right? If there's no ballistic mode, the right-hand side is 0 because you have nothing to project onto. And then what you say is that, well, that particular limit, as written there, limit t inverse and all that, is 0 on your two-point function. Okay. Now, so this is, so it's a large time limit at small wave number. And if you were to do the inverse Fourier transform in x and t, you'd find that the result essentially goes like 1/x or 1/t. It's a 1/t type of scaling. Okay? But if you do the inverse Fourier transform, in fact, you have to be careful, and you might find some 1/t with some delta functions on distribution, and then so it doesn't tell you the exact decay of the corresponding. It will tell you the exact decay in terms of averaging over fluids here, and the proper formulation is really that one that's written there. Okay. So that's the thing. So and here the subtlety is the space of conserved charges. So what is the space of conserved charges? And this is what kind of connects with this idea of the tori, being a bit less trivial in statistical mechanics. So the space of conserved charge here is a well-defined mathematically. This is a kind of a theorem. So within quantum stat mech, with all the little assumptions and all that, but it works for any quantum stat mech model with local Hamiltonian and finite local spaces. Okay. So there's an inner product that you have to construct in order to define these extensive conserved charges. The inner product is just very simply the space integrated connected two-point function. So that makes sense since this connected two-point function decays fast enough, which it does in the ergodic state, or at least in many ergodic states. There's a slightly stronger condition that more than ergodic state should decay, but for instance, it does in thermal state, which decays. So once you have this inner product, well, you can then complete it to a Hilbert space. So you say, well, this is my bilinear form. In fact, you can write that for non-Hamiltonian operators as well with the dagger and all that. You can complete that to a Hilbert space. And once you have the Hilbert space, you can take the subspace, which is invariant on the time translation. And these QIs are formally a basis for that subspace. So this is with putting the bells and whistles on that gives you a precise definition of what is the space of extensive conserved quantities. So it's this QI that you obtain by from the inner product, which is the integration over space of connected two-point function. Okay. So it turns out that under this time averaging and all that, the formula makes sense, and that Hilbert space is what comes out. That's why you can do the projection of this. Okay. Now, this space contains all the charge with local density, naturally, so the ones which satisfy local conservation laws. Also contains all the quasi-local charges, and it's a complete space. Now, here I didn't put any citations about, but quasi-local charges have been studied by Prozen and Ilievsky in the concept of integrable systems, and this is contained in that. Okay. At kappa equals 0, one recovers a well-known decomposition formula, which generalizes something called the Mazur bound for the Drude weight, which is just basically the time average of a current two-point function, like space-integrated current two-point function. And the particular case is that formula, but kappa non-zero is really the hydrodynamic bit. It's like it's a wavelength which are not exactly zero, but which are of the order 1/t, except for being exactly zero. Okay. The space, okay, this is a bit more abstract. The space is the correct space of invariant. Is a tangent space in manifold of states, of ergodic states. But this is not a theorem. This is what I think is the correct mathematical structure behind that. And it's kind of the right space to describe your invariant tori, if you wish. So it's really the thing that replaces your invariant tori in quantum statistical mechanics. Okay. Now, in interacting non-integrable system, Q is expected to be finite dimensional. Integrable system, it is infinite dimensional. And it turns out that this equation, this quantity can be shown to satisfy hydrodynamic equations. So it's not just a projection that one has, but also the full hydro equation. But I want to get to the other thing, so the generalization of that. So all this can be generalized to arbitrary frequency and wavelength, because our ergodicity we have at arbitrary frequency and wavelength. Okay. So what we can do then instead is take the time average with omega and the total space integral with wave number k. And then what you do omega and k. And k is disturbed by a small kappa over t. That's the Euler scaling around omega k. So instead of being Euler scaling around k0, omega 0, it's around omega k non-zero. You do Euler scaling. So you modify your k by a small thing. And then you see what happened. And it turns out that we have the same result. So basically, so here you have k is a small, a bit modified. So you look in the kw space on the right hand side is you look at the point k omega, but with k small a little bit change by an amount which is 1/t, and you want to see how things approach the k omega point as you do 1/t. And it turns out it's the same formula. The whole structure mathematically is actually the same for every omega and k, and it works because of the omega k ergodicity. So you can you can write this equality. This equality is true under that limit with omega, and so time average with omega and space integral with the k, where all the charges now depend on omega k, the space, everything depends on omega k, but it's the same construction. And how it depends? Well, here the charges will be of the type e to the ikx, and they should be such that when you come with the Hamiltonian, you get omega times q. So they are not invariant. They are kind of covariant, they oscillate, okay? And the inner product has a k in it, and all that. And the full thing satisfies also a hydrodynamic equation, a k omega hydrodynamic equation. And simple examples of these things are actually the creation and annihilation modes in free theory, which depend on k. And so these creation modes will be non-trivial elements of that space for a given omega. And if you apply the formula, you get nothing else but the Fourier decomposition of your two-point function of free fields in terms of creation and annihilation modes. So this Fourier decomposition is nothing else but a hydro projection formula in this hydrodynamics around k omega. Okay, so this has to be quick, but I think putting short on time. So I'll stop that to just make the connection with some recent works. And sorry, I haven't cited everybody here, but some recent work on time crystals, which was just the case kappa equals 0 of what I've explained here. And so in conclusion, so ergodicity is understood in terms of statistical mechanics at infinite volume using time averages. So we have an understanding of what's happening within this Lie cone where of the spatial growth of the operator. It is at the basis of emergence of hydrodynamic projection and equations, and that's what for arbitrary frequency with number. And so it would be interesting to see what this is very abstract, but one can construct these charges a bit more explicitly. There are examples in the literature. So this is the theory that tells you what these examples, where they fit. And there's, we think, a real understanding of various oscillatory behaviors that have been seen in the literature in terms of such kind of charges and hydrodynamics at arbitrary frequency. And I will stop there, and thank you for your attention.
Okay, great. Thanks for the talk. We ran a bit over time. Are there any immediate questions?
Does this tell us anything about the broadening of the light cone, like how it broadens in time?
So that would be the next order effect. So my understanding would be that I'd have to generalize that not just to the ballistic component, but the diffusive or super diffusive or kind of next to leading order effect. And I think this is what you will tell you about broadening of light cones. So for now, no, it doesn't tell you about the broadening of the light cone front, let's say front. But that would be, I think, from the next order effects, which I think can be analyzed in similar fashion, but it hasn't been done yet.
Thank you.
Okay.
So for instance, it's known that so at omega k 0, there's standard diffusion. In certain cases, you have super diffusion. And it would be very interesting to see what kind of diffusive effect you can have at arbitrary omega and k. Supposedly, there's a lot of nice phenomenology that will occur there. Anyway. Other questions?
Okay, well, in that case, I think I'm going to stop the recording and then we can chat more informally.
Yeah.